Hey, what's going on? It is your boy Jay Bailey here, and I'm back with yet another video. And today we're going to do something a little different. We're going to do a pwn challenge today. And so the goal here is going to be develop an exploit. And before you get too excited, it's going to be a very basic exploit, but it is an exploit indeed, because all an exploit does is just simply forces the software to do something that the author didn't intend to do. And that's what we're going to do here today. So the challenge we're going to start with is called Jeeves, and this is the first one in HackTheBox's binary exploitation pathway. And I think this is a pretty good way to sort of get your feet wet into the binary exploitation game. And so let's go ahead and get started, because you know I can talk a lot. So just like in the other challenge, we're going to start by running file here, because we don't actually get any source code or anything. We only get the binary. And so we see that it's 64 bits. We see that it's pi, actually. We see that. We see it's dynamically linked, and we see that it's not stripped, and so that's great. So let's go ahead and look at the symbols for this binary, and let's see. So we see that they are using the gets function to, that's obviously going to grab our user input, and we see they're going to malloc something, right? We see they're opening some file most likely, and they're going to read the file. So we have somewhat of an idea of what's going on. Well, very somewhat actually. Let's go ahead and look at the strings really quickly. All right. And this is most likely going to be the prompt here. They're just going to say, hey, how are you doing? What's your name? And then we essentially put in our name, and they're going to say, hello, whatever your name is. Hope you have a good day. And then we see here, this is flag.txt. So obviously this is hard coded in there that they're going to open up this flag.txt file, and essentially it's going to print out the contents of that with this thing here. That's what I'm assuming, at least, and I believe I'm correct in that assumption. So and normally this is where I would open this up in Ghidra, because obviously we need to do some more analysis. But before I do that, I want to run checksec on this. And what this is going to do is it's going to check the different security mechanisms that are enabled on this binary. So if we run it on here, and you have to have pwn tools installed, otherwise I think you have to run it in a different manner. But essentially this is just Python script that does a series of checks on the binary. I think it's Python script. Anyways. All right, so we see that it gives us these things here, and these are the different security mechanisms that are enabled on the binary. And so we already saw earlier that this was a pi enabled binary. And so what that's going to do is it's going to make it so when you actually run the binary, the instructions are going to be at a different offset than what you experience every time you run it. And so I think it's a little bit clearer if I were to show you really quickly. So if I were to run this in GDB really quickly, and let me open up my, I have a NoPy executable that I also created. Oh, it's called .test NoPy. There we go. All right, so if I were to disassemble the main function here, if you see, every one of these instructions has a corresponding address to it. And what's going to happen is when I actually run the binary, these instructions, these addresses are actually going to be very different than what we actually see from right here. And so that is going to prevent us from doing something like this. If I were to try to set a breakpoint here, actually let me run it first. If I just run it really quickly, oops, I should have set a breakpoint first, right? Yes, I should have. Okay, let me break at the main function here, and actually you can already see it changed, because we ran it once already, and so now it has the actual different addresses in there. So now if I actually do disassemble the main function, it's very different than what we saw earlier, right? And so in contrast, if we were to do that in a non-binary, so I'll just show you really quickly that this binary doesn't have pi enabled, right? So if I were to do disassemble the main function here, we see that these addresses here look a lot different than what we saw in the other binary. And similarly, if we were to just break at the main function and I run it, these addresses are exactly the same as what we saw earlier. And so that's what pi is going to do. It's going to make it so the actual instructions have different addresses than when you actually run them. And so that's a pretty good mechanism to defeat some of our exploitation techniques. And so what's also pretty interesting though is that, and I just learned this today, it's very difficult, or you cannot set a breakpoint for this address here, because as you saw earlier, it's going to change, right? So if I try to set a breakpoint at that address and I run it, you can see we get this error here. And that's because, as I just showed you, that the addresses change. However, what's really cool about Jeff is that you can actually do pi breaks. Actually, let me get the address, and I want to do just before the call to gets. So if I do pi break and I give it the address I want to break at, and I do pi run, we see that we were able to actually set our breakpoint successfully. So that's pretty cool. So if you didn't know that, I didn't know that earlier, but it's something that I learned, and I'll send the link in the description below of where that article that shows me how to do that, and it also has a good explanation of pi and some other things as well. All right, so I kind of got a little carried away there, but so there were some other things in here, right? So there was NX here, and we I think we know what that is, but if not, it's going to make the stack non-executable. And what does that mean? Well, we talked about the stack before, right? That's where the local variables are, the arguments to functions, and all that good stuff in the return address. Historically, what you could do is, in the buffer overflow, you can essentially put shellcode onto the stack and point the instruction pointer, which will execute the next instruction. You can point the instruction pointer at your shellcode, and it'll essentially just run. And the reason why that works is because computers, they just know to execute instructions and process data. They don't really care about the fact that isn't the instruction that the original software create developer wanted you to do. It just says I see an instruction, I execute an instruction. So NX is going to prevent that, right? So when you have the NX bit set, it's going to say the stack is not executable, and so if there are instructions on the stack, it does not execute them at all. So that's a very good mechanism to sort of defeat that sort of buffer overflow. But again, those are something that we can get around. The stack canary, we talked about that again. That was in a previous video. All that is going to collect a random value on the stack, and when you try to do your buffer overflow, it's going to essentially mangle that stack canary. And when you try to return from the function, it's going to say the stack canary has changed. They're trying to do buffer overflow. Do not let them do it, and just exit the program. That's a pretty good mechanism as well. And then finally, there's RelRO. And if you recall, the function, this binary is dynamically linked. And so the addresses for certain functions aren't known until a certain point in time. And because of that, you have the addresses for the function are written in what's something called a global offset table after you execute a function for the first time. So after that happens, then the mapping for address to function is then created in this global offset table. RelRO pretty much makes that table read only, so we cannot make changes to that table, so it'll make certain attacks difficult. And so you see there's 4 RelRO there, and I think that stands for like relocatable read only. I'm not entirely sure, but I think that's what it stands for. Anyways, so now we have a pretty good idea of the security mechanisms. We kind of know what we are looking for, and when we look at this in Ghidra, so let's go ahead and open this up in Ghidra. Alright, so now we got the binary open up in Ghidra here. So before we get started, something I always forget to do for some reason is open up our sudo C here. It's not what I wanted you to open. Anyways, you'll see why it was named should work in a second here. Anyways, so this is our sudo C, and so actually, if anybody knows how to better use Sublime here, this is an example here. For some reason, I named it sudo C, and as you can see, it opened up the last file that I had previously had open, and also there's no sudo C here, so if I have to actually type in some stuff in there, and then when I hit save, did I hit save? I did. Okay. I have to give it the name sudo.c. But I would think that the fact that I gave it this argument, that it would automatically do this. I don't know why it doesn't do that, but it, if anybody knows how to get it to work, I'd like to know. Anyways, let's go ahead and get started here. So, like I said, this is going to be a pretty easy reversing here, but our goal here is to do the exploit. So let's go ahead and see what's going on. First, we see that this local variable is getting set to this is dead code value, right? So we're also going to rename that to is dead code, and then it's going to be equal to hex dead code, right? And so let's go ahead and do that here. All right, and so then we see that it just prints that out. It prints out some, you know, the prompt, right? And then we see it's going to ask for our user input. And so this local 48 is going to be our user input if I want to rename that, right? And then so essentially it's just going to be kids user input there. All right, and so then what happens next? It says hello, whatever you typed in. Hope you have a good day. All right, cool. Prints that out, and then we see it's gonna do some comparisons. Let me just print. I'll just printf. I'll just say message. Cause I'm being a little lazy right now. I'm sorry. I know I usually type out the whole thing, but the main thing is the whole reversing. We know what the message is. We know what's printing that out. All right. So what happens next? It's gonna compare its isDeadCode variable to hex 1337BAB3. And for those who aren't so inclined, that's hacker speak. And so that says leetbabe, LEETBABE. So pretty clever. I think this is pretty funny. So what it's going to do is it's going to compare these two, and if they're not equal to each other, which of course they won't be equal to each other because deadcode was set, you know, that's static, and we don't ever change that variable. At least we don't see it here. If they're not equal to each other, then we're going to jump here and essentially exit the program. So all of this right here is essentially dead code. Right? Because like it can never execute because dead code would never be equal to leetbabe, right? So it's essentially dead code. So the question then becomes, well, how the heck do we get this code to execute, right? There has to be some way, and there is, and that way is to some exploitation, some very basic exploitation. So let's go ahead and scroll back up to the top here. So what we're going to do is we're going to pretty much mangle the stack here. So we're going to smash the stack by just giving a whole bunch of A's. And we see that the user input is going to be lower on the stack than this isDeadCode variable. So what's going to happen is if we overwrite all these other local variables in here, we can then write whatever value we want into this isDeadCode variable. And I'll show you a little bit how that works in a second. But let's see exactly what's going on in here. So we see it's gonna malloc something. So we see this is gonna be our flag here, and I'm just saying that because I know that's gonna be our flag. So I'm kind of cheating a little bit because I did this already. So we see flag is gonna be set to this malloc variable there. It's gonna open it with this flag.txt, and then this is gonna be here obviously our file descriptor, and then it's going to read the file, and it's gonna place that into flag, and it's gonna read hex 100 characters because that's the size of the actual flag there, and then it prints it out. So I mean, I guess I don't know. I'll write it out for you. Well, actually, no, I won't write it out because it's not worth the time. so we know what it does, right? It's pretty much gonna print out the flag, and that's all it's doing. So we have to figure out how to, you know, execute this code. And I just said we're going to smash the stack and overwrite this isDeadCode variable. So let's go ahead and see how we do that first. So I'm gonna open this up in GDB again. All right, and so now let's go ahead and look at the main function again, and I'm going to actually stop this right here. So right after we call the gets function, I want to stop it right there, and I want to show you what the stack's gonna look like at that point. So let's go ahead and again, we're going to do pi break, right? Just as we did in the first time. I'm going to pi run this. So now it's going to ask us for our names. And now I'm just going to print out a whole bunch I'm going to give it a whole bunch of A's, but I'm not going to overflow just yet. So I'm just going to print out, I think that's a good amount of A's there. So let's go ahead and do that. And we see what the stack looks like after I've done that, right? So we see that there's all these A's on the stack. And we also see here's our dead code variable. So what we can do here is if we can find out how many A's to overwrite until we get to this dead code variable, we can essentially overwrite it. We can essentially put whatever value we want on there. So let's go ahead and go back into Ghidra really quickly. And let me show you how actually I ended up calculating it. And I think there's probably a better way to do this, but this way was pretty easy. So we see that it gives us some offsets here, right? So hex 48 and there's hex C. So what we can do here is simply subtract 48, hex 48 minus hex C, and that'll give us hex, or actually decimal 60. So there's 60 characters from 60 bytes from this user input to this dead code variable, right? So let's go ahead and put that to the test here. I'm going to go ahead and run this again, and this command is going to let me put the output of this Python command in there. So I'm going to print 60 A's, and then I'm just going to say plus 4 B's there. And this is pretty much just going to test whether or not, I think I actually have to do like this here. And this is going to test whether or not I can actually overwrite that value, and then we're going to overwrite it with what we actually want to, which is our elite babe there, right? So let's go ahead and do that. Hopefully no mistakes. It doesn't look like it. No mistakes, right? Yeah, actually, yeah, no errors. Okay. So it looks like we did overwrite it, right? So we have we smashed the stack with all those A's, and then we have now A, and then some B's there. So now when we actually go and compare, right? So when we go and we print out, it's gonna say hello, all of that. So it's gonna compare RBP minus 4, which is our dead code, with elite babe. So if we do, let's go ahead and examine as a string RBP minus 4, and we see that we have successfully overwritten that value, right? So now this is essentially going to compare 4 B's to elite babe. Now that's obviously still not going to give us code execution, but we know that we can control that variable now, right? So now let's go ahead and do this again. But instead of 4 B's, let's actually put in the actual values we want. Now the trick here is we can't just put in 1337 like that, because this is going to be a little endian, so we have to put this in reverse order. Endianness is something really, really crazy, and I hate it, but it's just something we have to sort of live with. So we have to put this in reverse order in order for it to actually do what we want it to do, or interpret it as we want it to. So now when we do this, ideally what's going to happen is it's going to have, again, 60 A's in there, and then dead code is going to be replaced with elite babe, right? So let's go ahead and put that to the test, and we see there it is, right? There's elite babe right there. And so that means when we run this, we can go to continue, it prints that out. So now this comparison, if I were to examine as a, we're going to do it as a hexadecimal this time. Whoops, I think I have to do like WX there. There we go. And there we go. So elite babe is in there now. And that's obviously going to be equal to that. And so we can, if we hit continue, it's going to continue running through. Actually, just to show you, we now are inside of the actual of this function, or that dead code that we saw earlier. So now we can just continue, and there it is. Please meet your acquaintance. Here's a small gift. And again, we don't have flag.txt, so it's going to open up with pretty much errors, but we were able to execute that dead code. All right, now here comes the part where you saw that I had that. I think you saw it earlier. I have this should work Python script, and I'm calling it that because, for all intents and purposes, this Python script should be all we need in order to get this thing to work. And so obviously this host and port is going to change, because when we start the instance, it's most likely going to be different, but everything else should be pretty much the same, right? So we're going to create our socket, we're going to connect to the host and the port, we're going to send the data to the, so we're going to send the data to the host, and then we receive some data, and then we're going to print it out. Should be pretty easy peasy lemon squeezy. That's not really what happens. So let me show you this craziness that goes on here. So now we have the IPs and ports correct. Why did I do that again? Darn it. Hopefully it just starts up. Okay, yeah, okay. It's doing what it should do now. Alright, so this is where I say that this Python code should work, but it doesn't work as intended, and I don't know why. So if anybody knows why, please let me know. Alright, so if I run this, alright, so it's going to, if we go into our Wireshark again, you see that it connects to it, right? It does the TCP handshake, and then we see that it sends our data there, and we even see that there's our elite babe. and for some reason it just hangs here. I have no idea why it hangs here. I've tried to do multiple rec v's in there, but nothing seems to work. It just hangs. But if I were to just control C out of that, then we see that actually it stops, and then we see that it sends the actual data that we're expecting it to send, which I have no idea why it does this. But if I just do this follow TCP stream, we get our flag. I have no idea what I'm doing wrong with in that Python script, so if anybody sees anything glaringly wrong with this, let me know. But anyways, that's pretty much it. So we were able to execute code on the host that was essentially dead, but we modified the dead code variable in order for that check to pass, and we were able to get the flag in an unconventional means. And that's pretty much it. So that's all there is for this video. If you enjoyed this video, you learned something new, if you give me a like, I really appreciate that. If you have any questions, if anything else unclear, please leave your questions in the comment section below. I'll get to them as soon as I can, which is pretty soon actually. If you enjoyed this video and you want to see more of this type of content, do not forget to subscribe, hit that bell icon to notify when new videos go live. See you guys in the next one. Peace out.